Hi all. So in this lecture we are going to look at the expression trees. So in the last class we saw how we can change a given expression from postfix form to infix form, and then we saw that how we can traverse the trees in different order. So in order traversal we first consider the left child and then root and then right child, while in post order first we consider the children and then root node, and in pre order we first consider the root node and then the children. So something similar we can do with expression trees, and expression trees are nothing but the trees arranged in such a way that the expression or the operator is in the root node. So whenever we have two operands and one operator, then the operator is always shown as a root node. Now in this case again there are different operands and different operators, but here we are not going to consider unary or ternary operators. We are only going to consider the binary operations, which is add, subtract or multiply, and then multiply is shown by asterisk, and then a division like this, or raise to. So raise to is here in the following expression. Raise to is stored as upward arrow, but you might see somewhere it is also shown as like this. So these are the main binary relations or binary operators that we are going to consider while building expression trees, because at the most we can have two operands, and then binary trees can take care of those two operands as two leaves of this tree. So if we have very simple expression, so let's start from this page. So I just want to start with very basic expressions. If I want to do x plus y, then I can have this plus sign as root of the tree, having two leaves. One is x and one is y. So these two operands are going to be the leaves of the tree, and then the operation or our positive sign or addition is going to be at the root location. And this is how we can show this particular expression. Now if we want to have the prefix order for this expression, then we can have the addition sign first, so root, and then children, so plus xy. Now if we want to do the postfix order, is the post order traversal of this particular expression tree, then we are going to, so this will be the pre-order traversal or prefix expression. And if we have to do the postfix expression of the same expression, which is x plus y, then the postfix will have first both the children, which is xy, and then the root. So xy plus will be my postfix expression, and plus xy will be my prefix expression, and the infix expression is how we usually write and evaluate the mathematical expression, which is x plus y. Now one thing we want to consider, that now we will have another tree where it is obvious that in case of expression trees, when you have multiple operations to perform. So if now I have something like this, x plus y divided by z. Now if nothing more than that is given to me, then I will first consider that we are going to consider then the priority of these operations. So first we are going to consider the highest priority, which is for the raise to, then lower than that is for multiplication, and division, and then after that the priorities for addition, subtraction, and after that the priorities for the equal to sign. So we are going to consider the priorities, but in this case again this is not very clear unless we give brackets here. So if we give brackets here, it is evident for us which is given more priority, or we can also follow the same structure and then we can decide which expression out of these two or which operators out of these two are getting evaluated first. So in this case, if we, depending upon how we place brackets, the meaning for the expression changes if it is the infix expression like this, where we have operands and then in between two operands we have the operator. But if we have prefix or postfix, then it does not matter, or we do not need any brackets, because it generates unique expression using prefix or postfix as traversal. So we will see that. So let's say in this case, if we have something without brackets, then we are going to follow the priority of operators, and then first thing we are going to do is division. So y and z, between y and z we are going to have division symbol. And once we are done with the division, then we are going to add x to this particular division. So then this division and x get added, and this will be my final tree for this particular expression. Now let's see, we add a bracket here. Then in that case, it means that x plus y needs to be evaluated first, and then in that case my expression tree changes. Now I will have something like this. Before division I need to add xy, so I will add xy, and then I will have this addition and z. In between this addition and z I have a division symbol. So you can see that even if the infix expression remains same, depending upon how we are putting brackets, the expression trees are changing. So in case of infix expression, it is this thing we need to take into consideration, that depending upon which operator and which operation has more weightage or which priority, depending upon that the tree structure is going to change. But now for the same tree, now this is two different trees are generated using the same infix notation, x plus y divided by z, depending upon whether y divided by z is calculated first or x plus y is calculated first, and then these two different trees are generated. But if we consider prefix notation for this tree, then prefix notation for this tree is, first we are going to write, so let me just have arrow in order to avoid confusion. So first we are going to visit root in prefix notation, so plus, and then the children. Now children is x, and then division, so we first write x. Now in case of division, again division is a root, so we are going to first visit division and then yz. So division and yz. So this is the prefix expression for this tree, and for this tree, for second tree, we can see that the prefix expression is, first again we are going to visit the root node, so which is division, then the children plus and z. Now plus is a root again, so first we'll cover plus, then the children of plus, which are xy, And now we will go to the second child of division, which is z. So we can see that in prefix notation, these two expressions, which sign is given more priority, whether we want to first do division or whether we want to first do addition, that is shown clearly. And so we do not need any brackets to differentiate this. So each prefix expression gives us unique opportunity to know which expression is solved first and which has given importance. So here we can see that first yz is solved and then x is added. Here first xy are added and then z is divided. So these two prefix notation, they generate unique prefix notations for unique tree. But if you now try to find the infix notation of this tree, it will give us x plus y by z for both these trees. Similarly, for postfix expression also, for each different tree we can generate unique postfix expression. So here if I want to traverse this expression in post order traversal, I can generate postfix notation. So let's start. So in postfix we first cover all the children and then root. So here the postfix expression will be, I will just write pf and here it was the prefix, so I will write pr. So first was the pr. Now in postfix expression or post order traversal of this tree, we can see that first we want to cover all the children and then root. So x, and then here the division also has children, so we will see x, y, z and then division and then plus. So the postfix notation will be, first we reach at root node, then we visit all the children, so x, and then we go at division symbol, it still has children, so y, z and then division, and in the end we have this positive sign. So this is the postfix expression for first tree. Then we will see the postfix expression of second tree. And again here we will first revisit root, but we will not write root. We will come to the child of the root. This is again a root. Then we will visit the child of this root. So xy and then plus xy, then plus and z, and then finally we have division. So plus and z, and finally we have division. So we see that again for both of these trees postfix expressions are different. So for first tree the postfix expression is xyz divided, division and then addition, while for the second tree the postfix expression is xy plus z division. So we can see that every tree can be uniquely represented by prefix traversal or postfix traversal, or in a prefix and postfix manners, but we cannot say something similar for infix. In infix we might want to depend on how we are putting brackets for the postfix expression. So here we will see one bigger example where we have x plus y and then we have brackets in place. So first we want to do addition of x plus y, and here this first, in the first square you can see that there is plus sign and then x and y we are adding, and then for that we are, after adding xy, then we are going to have raised to 2. So here we can see that for this particular addition we are going to have raised to 2, and then we are going to have this second bracket inside which we are going to do x minus 4. So again we have one tree representing x and 4 and negating 4 from x. And then once we do that, we are going to divide by 3. So this is the second tree generated by that, x minus 4 divided by 3, and this is x plus y raised to 2, and then both these subtrees are joined by the addition sign. So here we are going to have addition to both these subtrees. So in order to really decide which of these operations come first, we have to have good or we have to have it bracketed in nice manner in order to avoid any confusion. If we don't do that, then we can see that similar to something like this can occur. So if we just give x plus y, so here it looks like x plus y, and then division x plus 3. So if we do not have any brackets given, then in that case the same expression can be shown by 3 different trees. So first we are doing x plus y, and then we are doing x plus 3, and then we are dividing. So like first tree is representing x plus y divided x plus 3. Now second tree might be that first we are doing x plus y divided by x. So so this is corresponds to the first tree. The expression which is given by this is, again I will write the same example, x plus y divided by x plus 3, and the second tree represents that we are first doing division between y and x. So really what we are doing first is this, then we are adding that division to x, and then finally we are adding 3 to this. Then again for the third tree we can see that what we are having the same infix expression, x plus y divided by x plus 3, and in this case what we are doing is, looks like we are first doing x plus 3, and then we are dividing. So we are first doing x plus 3, so brackets, so this is important operation for us first, and then we are dividing it with y, and then we are adding with x. So this is for this particular tree. So we can see that the same expression, depending upon how we put brackets, it changes, and it is kind of confusing. So brackets are very much needed, or parentheses are very much needed when we are talking about infix notations, or when we are traversing the tree in order. So in order traversal of a tree gives us the infix notation. So here are some more examples of infix notations that we can consider. Is that if we have, like in the previous case we said, so this simple expression can also generate 2 different trees depending upon how we place it, like this, or whether we place the bracket like this. So in infix it is not straightforward until we know where the parentheses are. But the prefix notation and postfix notation, for each of the traversal, it generates unique notation. So if I have been given a prefix notation or a postfix notation, I can create a tree uniquely, so there will not be any confusion. So when we traverse the rooted tree in pre-order, we get the prefix notation, and the prefix notation is also called as the Polish notation. And here, if you remember the first expression, tree expression that we started with, and then how that notation can be changed. So if we go back and look at this particular tree, now not this one, okay, this tree. And now if we want to generate prefix notation for this, then we first visit the root node, which is plus, then we come on the left hand side, that is also root, so we write that raised to. Then we again come to the left side, it is also root node, so we write plus. And then when we cover this root node, then now we are going to cover the children of this root node, so we will write xy, so x and y. Then we cover this part. Now we are going to cover the right hand side, which is 2, so xy and then 2. And after that we are going to cover this particular root, and then we want to go to the right hand side. Now if we go to the right hand side, it has division. Now division is also root in itself, so we'll write division. Then it has two children, minus and 3, so minus is also root in itself, so we first write minus, then we take children of it, x and 4, so we first write x, then we write 4, then we write 3, and then we finally we cover the division, and then finally we cover the, I think we already covered this part. So we can see that every time we first cover the root node and then children. So for children, if you have children, then you cover those children, and then you cover those children, and then you go to the right hand side and then you cover all the children. So division minus x4 and then 3, and then that's all how the tree is covered. Now similarly, if we want to do, so here you can see it's the same expression they have given, and then prefix expression. Now if we have to evaluate a given prefix expression, then the evaluation is done from the right hand side to left hand side. So here is one different example, but another example. So if we have some prefix expression given like this, where it is plus minus multiplication, then 2 3 5 division raised to 2 3 4, then what we do is we start from the right hand side, so 3 4, but we cannot evaluate 3 4 because we do not have any operator. So we come on the, so we shift on the left hand side, starting from the rightmost, we go on moving toward the left hand side. Then another two operands we can choose is 2 3, and then there is an adjacent operation which is raised to. So 2 raised to 3, we evaluated 8, and then this whole part, we instead of this whole part, now we substituted 8. Now again we started from the rightmost part, and then we have now 8 4 and division. So we can evaluate this, we can say 8 divided by 4, and then we get 2 here. Now we substitute 2, so we remove this part and then we substitute 2 here, but we cannot evaluate 5 2 because here there is no operator. We cannot evaluate 3 5 because preceding is not an operator. But for 2 3 we can evaluate 2 3 because we have multiplication symbol before 2. So now we evaluate 2 multiplied by 3, we get 6. Again we remove this part and then we substitute 6 in place of these 3 things. So we substituted 6, and now again we start from the rightmost. Now 2 5 we cannot evaluate because we have a number 6 here, but 5 6 minus we can evaluate because minus 5 6 we have 6 minus 5, and after evaluating this we get 1. We substitute 1, and now 1 2 plus, so we do addition between 1 and 2 and we get the final answer as 3. So the most important thing to remember is that we do not solve it like the way we do for infix. So basically we start from the rightmost a rightmost number, and then we keep on finding the operator. So whenever we find operator, then we take next two operands and then we evaluate. And so starting from the rightmost, we go backwards to the left hand side while solving the prefix expressions. Now for the same tree, we wanted to find the postfix expression, and then we know that for the postfix expression, we want to, so for the postfix, we want to do children and then root. So we start from plus, then we go to the raise 2, then raise 2 also has two children, then we go to the plus sign has two children. Now these are leaf nodes, so we first write those and we write, so this is for the postfix x, y, and then we cover the root which is plus, and then after we cover plus, we have to cover the right hand side which is 2, and then we cover the raise 2, and then we have to cover on the right hand side children. So we come here, it is a division, then division has two children, minus and 3. Now minus has two children, x and 4, so we do x4 minus, so x4 minus, and then minus 3 division, so minus 3 division, and then at the last we are going to cover the plus symbol. So for the same tree, we found the infix notation, then we found the prefix, and then we can also find the postfix notation by doing post order traversal of this expression tree, and then we get the postfix notation. Now things that we need to remember for postfix expression is, when we want to evaluate, again we are going to only consider the binary operators here. We are not going to consider unary operators. So whenever we find operator, we need two operands to solve that given operation. And similar to postfix notation, this give us unambiguous and unique expression. So whenever I have any postfix expression, I do not need any parenthesis here. I can evaluate it, and then I will always get a unique number or unique answer. And here we do not need to know, because this is the way they are arranged, is that it is always a unique expression. So what we do here, when we have to solve postfix notation, it is the other way around of prefix. So in prefix, we started from the right hand side and then we came backwards towards the left hand side of the expression. While solving postfix, we start from the left hand side. So here 7 to 3, we are going to look for the operator. So first operator we find is the multiplication, and now for the multiplication, we have to consider two previous operands. So the two previous operands are 2, 3. Now we can evaluate this expression, 2 multiplied by 3, and we get the value 6. And now I'm going to, so we want to remove this part now, and we want to replace this part by 6. So next I have 7, 6 minus, and then the remaining expression. So the next operator is minus, and the previous two operands are 7, 6. So 7 minus 6, we get 1. Again replace this 3 by 1. So next we will have 1, 4 and raise 2. So 1 raised to 4, we get 1. Again replace this 3 by 1. Then we get 1, 9 and 3. Now 3 is not an operator. So we have to find the next operator, which is division. Then take two previous operators, 9 and 3. So we do 9 divided by 3, we get 3. So replace these three things, 9, 3 and minus by 3, which is the answer. So we are basically getting rid of all these things. So by 3, so now I have 1, 3 and plus. So we can solve it by 1 plus 3 and we get answer as 4. So this is the way we solve postfix expression. So we have to remember that while we are solving prefix expression, we come from the right hand side towards the left hand side, and in postfix we start from the left hand side, and then we find operator, we take two previous operands, and then we solve, substitute the value, again find for the leftmost operator, take two previous operand values, evaluate that, and so on, and then finally we are able to solve the postfix notation. So these two things are very important, how we want to evaluate it, and then in the which direction. So don't forget the direction. Direction in prefix you go this in this direction, and in postfix you go from left to right. So next important topic is spanning trees. And in spanning tree, what we mean by that is we are looking to generate tree from graph. So mostly we will be given some graph, and from that graph we have to find tree. So whenever we are violating the definition of tree, that time we have to stop. So you can see there are two ways of generating spanning trees. So first let's consider this G as a simple graph given here. So you can see that G has circuits or cycles. So A, B, F, E, A is one cycle, then F, C, G, F is another cycle, E, F, G, E is third cycle. So that is allowed in any graph. But when we have to find spanning tree from this graph, what we want to do is all the vertices should be there. So what are the vertices of original graph? Those vertices need to be there in the spanning tree also. But whenever it is generating cycle, that particular edge we need to remove, because in a tree we cannot have cycle. So if we keep on removing such edges, then we can finally we can find a tree, and then that tree is called as spanning tree. So the graph is connected, but this graph is not a tree because it has some simple circuits. So we will see which edges we need to remove. Now again, there are different ways of doing that. Somebody might want to remove this edge, and then this A, B, F, E, A, this circuit or cycle is broken. Another person might remove this edge, and then still it will be broken. So you can do, or you can create spanning tree from a given graph in multiple ways. So here one way they have considered is that you remove edge AE. So the graph will look something like this, where you have this particular cycle is removed, but you have two more cycles, CFG, CFGC, and then you also have EGFE. Now to break EFGE, they remove another edge EF. Now this cycle is also broken. And then another edge needs to be broken to break CFGC. So they remove, let's say, CG. Again, different people can remove different edges, and that is fine as long as we are still getting a spanning tree. Then they remove CG, and when these three edges are removed, we are basically breaking down these three cycles, and then the resulting graph that we are getting is a tree. So this is called as a spanning tree, which we derived from a given simple graph. Now a simple graph is connected if and only if it has a spanning tree. So if after removing the cycles, if we get the graph as a disconnected, then we cannot call that graph connected in the first place. So why is that a proof? Because let's consider that we have a graph, and then that graph G has a spanning tree T. So T needs to have every vertex of G, and the edges of T will be subset of edges from G. Then if if it is so, then there is a path in G between two of these vertices. So if if in T there is a path between any two vertices, then in G there should be a path in between these vertices, and we know that tree is a connected structure. So if T is a connected tree, then the original graph, it also has to be connected. So suppose if G is a connected graph but G is not a tree, it contains a simple cycle or circuit, and if we remove that one edge from that simple circuit, then the resulting subgraph is going to be still connected, because all the other vertices can still go from one vertex to another vertex. So if you consider here, even if we remove AE, we remove this particular edge, we still have a way to go from E to A. We can traverse E to F, we can go from F to B, and we can go from B to A. So the resulting spanning tree is still a connected tree. And similarly for the remaining circuits as well, even if we remove the edges, we still have a way to go from C to G. We can go from C to F and F to G. Then here we can still go from E to F, we can go from E to G and G to F. So this graph still remains a connected graph even if we remove the edge which was making circuit. So a tree produced because of removing such edges which were making the cycles, the resulting spanning tree, what we are getting, is also connected graph. So in this next few slides, we are going to consider two techniques for creating spanning tree. So first technique is called as a depth first search, meaning that keep on adding depth wise, then the tree will grow in the depth first search manner. So here we are going to see one example, and then we are going to continue doing this until we cover all the vertices of a given graph. So here is one graph given to us. Again, there are two cycles here which we can see, DEF and FGH, and then like in the previous case, we can remove either of one edge and get the spanning tree, but we don't want to do that in this case. In this case, we want to start from one vertex and we want to go depth wise, how many vertices are attached to that, and then that vertex is attached to how many other vertex, and so on. So actually I did consider some thinking about the breadth first. So in breadth first, you will first consider all possible vertices connected to that vertex, and then for this vertex again we are going to consider all possible vertices, and for this we are going to consider all possible vertices until we find cycle. And in depth we are going to consider for this what was the so let me just do it again, or maybe I will do it for this example. So we start from vertex F. So let's say this is vertex F. Now we are going to consider what is the other vertex which is connected to F. So we might want to consider the next vertex at G. Now here is, am I going to consider any cycle or is it creating any cycle? No. So I can add G. Now what is the other vertex that is connected to G, which is H? So I can keep on adding H. So this is growing depth wise. Now I'm not considering the other vertices that F is attached to at this point. When I cannot move any further, that time I will go back, I will backtrack, and then I will see what other vertices I can. Now from H, I will check what are the other vertex I can reach to. I can reach to K. So here I am just going depth wise, I am considering one option at a time. So I reach to K. Then from K, what are other vertices I can reach to? I can reach to J. So from K, we come back to J. Now at J, it's kind of an end point. I cannot go to any further. I can only go to K, and K is already covered. So we are not interested in going or drawing the edge KJ again. So we will backtrack and we come back to K. And from K, I'm getting only H, which I have already covered. So again, I will come back to H, and then I will consider, is there any other option that I have from H? And from H, I have HG, but I can also go to H and I. So that point now I want to cover, because this is the new vertex I'm getting. So HI, I will make a part of this particular tree. Then if I cover I, then from H again I cannot cover F, because that will make a cycle. So next thing what I can do is so this is the only thing I can cover, G and I, which I already did, and I will not cover FG, so FH, because that will give me a cycle, so I don't want to do that. Now I backtrack, I go to G, and from G what else can I add? I have already added F, I have already added H, so that's what I can do. Now I backtrack to F and I come back to F, and I see, are there any other vertices that I can cover from F? So from F I can also go to D. So this is the next vertex that I can cover, and I can say D. Then I come to D, and from D what are the other vertices that I can cover which were not covered previously? So I can also cover E. E is not covered in our tree, and we have a line from D to E, so I cover E. Then what is the other vertex I can cover from E? From E I can go to C, so we cover C here, and then from C I can cover both the remaining vertices, which are A and B, and I think that's all. So at this point we have covered all the vertices of the graph without taking into consideration the edges, creating the cycle. So this is how the tree is generated by doing depth first search. So you pick one vertex, you go up till the longest path that you can reach, and then when you cannot move any further, you can go in the backwards direction, and in order to just check which are the more vertices I can go on adding in this particular tree. Now the another approach that we can use to generate spanning tree is called as breadth first search, and this is a small algorithm for depth first search, that you visit the vertex W, which is adjacent to V, and if it is not in T, then you add vertex W and edge into T, and you have to make sure that T is a tree always, so you cannot add any edge which is creating cycle. Now in breadth first search, as we saw, we pick one vertex and then we consider all the possible vertices that we can reach from that vertex in level 1. Then when we are done with all, we go to the level 2. So we go on this vertex, how many vertices we can reach, from this vertex how many vertices we can reach, and we are covering the vertices in the breadth first manner. And again we continue till the point where we cover all the vertices without including the edges having or making the circuits. So here a different graph is given, and then we can choose any arbitrary node as a root node, but here they have chosen E because E has the highest number of vertices that we can cover in the breadth first manner. So again starting from the E, we are going to cover all the edges and all the vertices which can be reachable from E. So this is E, then from E I can reach to B. I can also reach to D, F and I. So there is this edge, I can reach to D, I can reach to F, and I can also reach to I. So this is the maximum, these are the maximum 4 vertices that I can reach to E. And randomly any vertex you can choose, and then you can generate a tree, and you will almost always end up covering all the vertices. Now we cover breadth wise, starting from the next vertex B. Again we will check what other things we can cover. E we already covered. So the other 2 vertices which we can cover from B are A and C. So we can have here A, vertex A, and then vertex C. Okay, from D we can also cover A and E, which we have already covered, so we don't want to cover the same vertex again. Then new vertex we can cover from D is H. So we just want to add the newly reachable vertex, which is H. Then we go to F and we check from F what are the new vertices that I can add into this tree. I can add C, but if I connect F and C, I will generate a cycle here, and this vertex is already covered, so I am not interested. I am looking for something new. So C is already there, E is already there. I can add J and G, which are 2 new vertices I can reach from F. So one is G and another is J. Okay, moving forward to the next vertex, which is I. Now we are going to check from I what is the new vertex I can go to. E is already covered, H is covered, J is covered, K is the new vertex I can go from I. So I go to K. So now we are done with the level 2. So at level 1 we could reach to B, D, F, I. At level 2 we could reach to A, C, H, G, J, K. So we will keep on doing that until we finish visiting all the vertices. So but we are not finished visiting all the vertices. We are still left with L and M. So from A we cannot reach to any newer vertex. So we already have B, E and D. From C we cannot go to any newer vertex. We already have B, F covered. Then for H again D, I, K all are covered. For G though we can go to another vertex which is not covered, that is L. So from here G we are going to cover that new vertex which is L. From J we cannot reach to any newer vertex. G and I are already covered, and F is also covered. Then from K we can reach to a newer vertex which is M. So from K we are going to write a new vertex M, because there is an edge Km that we can add. And this is the tree generated using breadth first search on this diagram. Now again you might say that using depth first search and breadth first search, we do come up with the trees which are not looking like a original graph, but that is fine. The first thing we learned in graph that no matter how you show it, as long as there is a connection between A, B, and that is also shown in this particular tree, we are still getting a valid spanning tree using these 2 techniques. Now if we want to look for the pseudocode for breadth first search algorithm, then we are going to consider T as a tree, and then we are going to start with a particular vertex V1 in list L, and then while list L is not empty, we are going to remove the first vertex V1, and for each neighbor of V, we are going to add that each neighbor W of V, we are going to add it into L, and we are going to visit that W, and then we want to add that H into tree if it is not already there, and so on. So we are basically traversing the tree in the breadth wise manner. So here is some more examples of trees where sometimes we want to change it, and we want to take some hybrid approach where we are using both depth first search and breadth first search simultaneously. So in this case, for this particular graph, we can see that this graph is a directed graph. So here now we also have to take care of directions. Now we cannot say that A is reachable from B and B is reachable from A like we did in the previous case, because that was undirected graph. So no matter how we traverse, it was okay. But in the directed graph, we can go from A to B, but we cannot go back from B to A. So again, if we start from particular vertex A, then we can go to B. From B, we can go to F and C. So we go to F and C. From C, we can go to G, and then from F, we can go to E. Okay, and then here we are kind of stuck, because from E, we cannot go anywhere else. Because all the arrows are incoming to E, and for G also we cannot go anywhere else because all the arrows at G are incoming arrows. So we are kind of stuck here and we cannot progress further. So what we can do is, now we start with another vertex D, and then we see that we can go to H, so we can cover this part H. From H we can go to L, then we can go to K, then we can go to J, and so on. So when we cannot find any new path, we return to A, and then we will start or begin a new tree from a new vertex which is not already there in our covered tree, and then we will generate a new tree in this way. So maybe we will get something like this. So in this case the tree is not connected, but this is what we could get. And then we saw that here we are really doing or beginning another tree with D, and we find this new tree consists of this particular given path. And again, I was not covered by this tree as well, so we just wrote I as it is. And then we added another tree which only contains I, which is its root. So sometimes when we have typically with direction, it is not that straightforward to get a connected tree. So sometimes we can get components like this, in which we can end up having forest instead of tree, because we do have connected components, but we do not have a single tree. So this is also called as a spanning forest instead of spanning tree, because here we are getting different components as a part of this tree. So whenever you have seen web crawler, or we reach to one website, and from there if we want to generate or we want to gather similar websites having similar meaning and things like that, so in that case they do have approach which is a combination of depth first search and breadth first search, and then we can explore it and then find possible web pages which have similar meaning than what we are searching for. And those such programs are also called as web spiders, where there is a starting point and then they grow and then they find the web pages which are similar in meaning, and then those are implemented in websites as in Google.